For our unconventional computing project, we have decided to make logic gates, half adders and full adders out of magnets. A logic gate is an idealized or physical device implementing a Boolean function. That is, it performs a logical operation on one or more logical inputs and produces a single logical output. Adders are digital circuits that perform addition of numbers. We'll be splitting this video into two sections, logic gates and adders. Logic gates are primarily implemented using diodes or transistors acting as electronic switches. With amplification, logic gates can be cascaded in the same way that Boolean functions can be composed, allowing the construction of a physical model of all of Boolean logic, and therefore all of the algorithms and mathematics that can be described with Boolean logic. These gates are the AND, OR, NOT, NAND, NOR, XOR, and XNOR gates. Our logic gate design consists of two electromagnets powered by DC power from batteries. One of the electromagnets is held into position by clay, and there's a limit switch attached to it. The regular switch represents the input. The 1 and 0 on the regular switch represents true and false respectively. Turning on the electromagnets will attract the other electromagnet, hence engaging the switch. When the two contact surfaces meet, this will form a complete circuit which will turn the output of the logic gate on. This output is fed to a LED, thus switching it on. When we switch off the electromagnet, it will cause the limit switch to spring off, hence pushing the other electromagnet away and breaking the circuit. This turns the output of the logic gate off. Logic circuits include such devices as multiplexers, registers, arithmetic logic units, and computer memory, all the way up through complete microprocessors, which may contain more than 100 million gates. Now, we will be demonstrating our logic gate constructs, starting with the NOT gate.
NOT gate. A NOT gate, often called an inverter, has only a single input with simple behavior. A NOT gate performs logical negation on its input. If the input is true, then the output will be false. Similarly, a false input results in a true output.
NOT gate. When the input is 1, the output is 0, and the LED remains switched off. When the input is 0, the output is 1, hence the LED switches on.
AND gate. An AND gate is a digital logic gate. The output of an AND gate is true only when all of the inputs are true. If one or more of an AND gate's inputs are false, then the output of the AND gate is false.
AND gate. Starting at an input of 0, 0, the LED is off. An input of 0 setting the input to 0, 1 as well as 1, 0 both keep the LED off. When the input is set to 1, 1, the LED turns on, an output of 1.
NAND gate. A NAND gate is sometimes referred to by its extended name, negated AND gate. The output of a NAND gate is true when one or more, but not all, of its inputs are false.
NAND gate. The input is started at 0, 0, which means the LED is on, meaning an output of 1. Input 1, 0, the LED stays on, an output of 1. For input 0, 1, the LED stays on as well, also an output of 1. Input 1, 1 turns the LED off, meaning an output of 0.
OR gate. An OR gate is a digital logic gate. The output of an OR gate is true when one or more of its inputs are true. If all of an OR gate's inputs are false, then the output of the OR gate is false.
OR gate. Input set to 1, 1 sets LED to 1, returning an output of 1. Input 1, 0 keeps the LED on, and the output stays as 1. Input 0, 1 keeps the LED on as well, and the output is still 1. When the input is 0, 0, the LED turns off, representing an output of 0.
NOR gate. A NOR gate, sometimes referred to by its extended name, negated OR gate, is a digital logic gate. The output of a NOR gate is true if all of its inputs are false. If one or more of a NOR gate's inputs are true, then the output of the NOR gate is false. NOR gate. The input is started at 0, 0 and the LED is on, meaning an output of 1. Input 1, 0 turns the LED off. Input 0, 1 turns the LED off as well. The LED is off for input 1, 1. All three of the previous inputs have an output of 0. XOR gate. An XOR gate, sometimes referred to by its extended name, exclusive OR gate. The output of an XOR gate is true only when exactly one of its inputs is true. If both of an XOR gate's inputs are false, or if both of its inputs are true, then the output of the XOR gate is false.
XOR gate. The input starts at 1 0 where the LED is on and the output is 1. An input of 0 0 turns the LED off and the output is 0. Input 0 1 turns the LED back on and the output is 1. Last, the input 1 1 turns the LED off again, which is an output of 0.
XNOR gate. An XNOR gate, sometimes referred to by its extended name, exclusive NOR gate. The output of an XNOR gate is true when all of its inputs are true, or when all of its inputs are false. The output of the XNOR gate is true when both of the inputs are the same.
XNOR gate. The input starting at 0 0 has the LED off and the output is 0. The input 1 0 turns the LED on and the output is 1. Input 0 1 turns the LED on as well and the output is 1. Input 1 1 turns the LED back off and the output is 0. Next, we will be moving on to adders.
In electronics, an adder or summer is a digital circuit that performs addition of numbers. In many computers and other kinds of processors, adders are used not only in the arithmetic logic units, but also in other parts of the processor, where they are used to calculate addresses, table indices, and similar operations. Half adder. The half adder adds two single binary digits A and B. It has two outputs, sum and carry. The carry signal represents an overflow into the next digit. To represent the output, two LED are used. The yellow LED represents the carry bit and the red LED represents the sum bit in the output of the adder. Half adder. When the input is 0 0, the sum is 0, represented by both LEDs off. Input of 0 1 and the input of 1 0 both have a sum of 1, which is represented by the sum LED on. The input 1 1 has a sum of 2, or 1 0 in binary. This leading one is represented by the carry LED on and the sum LED is off.
Full adder. A full adder adds binary numbers and accounts for values carried in as well as out. A 1-bit full adder adds 3 1-bit numbers, often written as A, B, and a carry in. The carry-in bit is used when more than one full adders are linked together to handle multi-bit input. Here the carry-in bit is the leftmost switch. It has two outputs, sum S and carry C. The carry signal carries the overflow into the next linked adder. To represent the output, two LEDs are used. The yellow LED represents the carry bit and the red LED represents the sum bit in the output of the adder.
Full adder. First, the carry-in bit is set to 0. An input of 0 0 0 has a sum of 0 where both the LEDs are off. An input of 0 1 0 has a sum of 1 shown by the sum LED as on. Input of 0 0 1 also has a sum of 1 and the sum LED is also on. An input of 0 1 1 has a sum of 2 or 1 0 in binary shown by the carry LED as on and the sum LED as off. Next, the carry-in bit is set to 1. An input of 1 0 0 has a sum of 1 and the sum LED is 1. An input of 1 1 0 as well as an input of 1 0 1 has a sum of 2 or 1 0 shown by the carry LED as on and the sum LED as off. When the input is 1 1 1, the sum is 3 or 1 1 in binary shown by both the carry LED and the sum LED as on.
In conclusion, there are many applications of logic gates and adders. For adders, it is even possible to create a logical circuit using a series of full adders to add n-bit numbers. The full adders are chained together such that the carry-out bit of one adder is connected to the carry-in bit of the next adder. The carry ripples from one adder to the next similar to the pencil and paper addition. This is known as a ripple carry adder. Note that the least significant full adder may be replaced by a half adder if under the assumption that carry-in equals to 0. An example circuit which uses logic gates and adders is the arithmetic logic units. The ALU is a digital circuit that takes in two multi-bit numbers and performs integer arithmetic and logical operations on them. It is a fundamental building block of the central processing unit of a computer, and even the simplest microprocessors contain one for purposes such as maintaining timers.